Everyone, welcome to another Select seminar. Today we have Matthew Sutcliffe from the University of Oxford who will be talking to us about a dynamic T-decomposition for classical simulation of quantum circuits. So please, Matthew.
Yes, okay. So this will be a talk based on this recent paper, um, which was co-written with Weira, who was my master's student last year, and this is kind of an extension of some of the work that he did in his master's thesis. And the idea here is to come up with new decompositions for classical simulation, but which are more dynamic. And I'll explain what that means as we go ahead. And just a brief thanks to Alex, because we bounced some ideas off of him in his office in the early stages. And I'll kind of mention again at the end where he was helpful to us. This paper's up on the archive, so if you're interested, you can check that out. And it's quite a small paper, so there's not much new work to talk about. So it'll probably be quite a brief seminar this week, but I'll try and cover a lot of the background to try and make it a bit more in depth. So firstly then, what is classical simulation? So we split this up into two types we call strong and weak simulation. So the former is essentially where we have some circuit with inputs and outputs, and we want to know what is the probability of measuring these particular outputs. And in terms of ZX calculus, this would just amount to plugging your inputs and outputs with states and effects. And then you have a scalar ZX diagram, which is just equal to a scalar. So if you can reduce this down, it'll just come out with a number. And then the absolute square of that number tells you the probability that you'd measure this. And then weak simulation, on the other hand, is where we essentially want to emulate a quantum computer. So we have some circuit, we provide it with inputs, and we probabilistically sample some kind of output according to the actual probability distribution that the quantum computer would have. So these are the two things we might mean when we refer to classical simulation. As you might be able to tell from these definitions here, strong simulation kind of implies weak simulations. So you can do weak simulation through applications of strong simulation. So in this paper, we focus on strong because being able to optimize strong means you're optimizing weak as well. Okay, so then why do we want to do classical simulation? What are the uses? I'll just very briefly kind of highlight these. So we want to have verification of quantum algorithms. So if you can run your quantum algorithms on classical hardware, you can verify that the results you're getting out are actually correct on what you'd expect. Likewise, you can verify your quantum hardware in the same way. Is it behaving the way you want it to? So you can compare it to how it would behave classically, and you can see that the results are the same, up to some kind of noise. Measuring the quantum advantage, this is a big one. So if you're running your quantum algorithms on quantum computers, it can be very handy to know, if you were to run the equivalent algorithms classically, how much improvement are you actually getting from the quantum advantage from having these quantum computers? So you can run it on classical hardware and quantum hardware to measure this. Simulating many body systems, likewise. There's hybrid algorithms as well, which use parts classical, parts quantum. The overlay is on that, so I can't quite see it. But something about cryptographic security, analysis of cryptographic security. So it's quite handy to analyze these kind of systems. And then there's a handful of more use cases. But the point is, it's a useful thing to be able to do. Okay, so I mentioned that we can do weak simulation through strong simulation. So just briefly, how does this work? Well, we consider something called marginal probabilities, which is where we're concerned with the probability of part of the outputs. So instead of saying what's the probability that we have this particular output on all the qubits, we just concern with an output on some of the qubits. And then we can kind of build that up. So we probabilistically sample the first qubit, and then we use that to probabilistically sample the next qubit, and so on. And this is how you can build up a weak simulation. And these are the two methods really for doing that. You have the summing method, which is what I just mentioned, where you just kind of you sum up all the probabilities over all the outputs, and that tells you the probability over those qubits, right? And then the other method then is to use a bit more ZX, and you double your graph. So you compose it against its own adjoint. And the benefit of this is that you don't have to do this big sum, which could be exponential. Well, is exponential with the number of qubits. But you do double the T count, although using ZX like rewriting, you actually don't quite double it, you reduce this. So when you want to do the summing or the doubling method depends on essentially what I'm calling K here. So how many qubits are you actually concerned with the output of? Um, yeah, so these are the two methods. You can kind of bounce between them depending on these particular metrics. So then where does ZX calculus come in more concretely? So you can express any circuit as a ZX diagram. We're all familiar with this because this is the ZX seminar. So not to bore you, I'll add a giblified version of the rewriting rules there. So essentially, when we have our ZX diagrams, our quantum circuits, which we want to measure, so we have them as scalar circuits, and we translate them to ZX diagrams, and we just simplify them using the rewriting rules. If it's Clifford, so that means all the phases are multiples of pi over 2, then it'll just fully reduce to a scalar, and we take the square, and that's the probability. If it's not Clifford, so if you have T gates, which we do need to be able to approximate, any quantum algorithm, then we don't quite get that far, and we end up with circuits that look a bit more like this, where it's just filled with these T gates, which are odd multiples of pi over 4. And no more rewriting will get rid of these. So then we need to introduce the idea of decompositions. And there are other ways to solve this. You can use tensor contraction, but this is what we're concerned with here, is stabilized decomposition. So if we look at the definition of Z and X spiders, we can derive this simple decomposition where we can translate a Z spider into a sum of two X spiders, or an X spider into a sum of two Z spiders. And then we can generalize this slightly to apply it to any phase. And so just with these slight generalizations, it allows us to translate any T-like spider into a sum of stabilizer terms. And we'll just label these metrics here, eta and tau. So eta is the number of terms that it decomposes to. So in this case, it decomposes to 2 terms. And tau is how much T-count reduction you get from each application. So in this case, these 2 resulting terms have 1 fewer T-count than this left-hand side. So this is 1. So what this means is if you have a big Clifford T ZX diagram with a T-count of T, then you can just keep iteratively applying this to reduce it into fully Clifford. So in the first case, you'd reduce it into 2 ZX diagrams that each have 1 fewer T-count, and then each of those gets reduced into 2 ZX diagrams with 1 fewer T-count. So you end up with this big decomposition tree where it grows exponentially the number of terms you end up with. Yeah, so you end up with eta to the T over tau terms, which in order to compare different decompositions with a single metric, we generalize this to 2 to the alpha T, where alpha is the metric of how effective this decomposition is. And n is the number of terms you end up with, which is more or less proportional to the runtime. So that's the thing we're trying to minimize. Okay, so 2 to the alpha T is the theoretical scaling that you'd get, but actually, as John and Alex pointed out a couple of years ago, that every time you apply one of these decompositions, so you go from this G to G0, for instance, before you apply the next one, you do a round of full simplification with ZX calculus. And this can actually remove some of the T gates, so it actually reduces the T count at each step, just with a little bit of rewriting, just essentially free computationally. And so the actual number of terms you get out is better than what you would predict just from these alphas. So we measure this with alpha EFF, so the effective alpha, which is to say we consider how many terms it actually reduces to, and then we backwards calculate what's the corresponding alpha of that. And this is always going to be less than or equal to the normal alpha because it's using simplification at each step. Okay, and then most of the literature has been focused on improving the efficiency of this approach by finding new decompositions that have lower alpha. And that's a reasonable assumption because, as I mentioned, if the alpha is lower, then you'd expect, the decomposition would result in fewer terms and that would speed up the runtime. But actually, it's the effective alpha that is more important. So kind of the thesis of this paper is more about how we can find decompositions that are focused on improving the effective alpha rather than the immediate alpha. So we're trying to predict how much simplification will be facilitated by these decompositions. Yeah, so some of the literature so far, as I said, so that example decomposition, this one here, is quite poor. And these better ones here have lower alphas, so 0.47. And this one on the right is the current state of the art for a decomposition that's generally applicable. So you can apply this anywhere you have five or more T-spiders. So asymptotically, it's applicable anywhere you have T-spiders. But then there are structure-specific ones, like these cats decompositions, which have lower alphas, but they rely on specific structures. So you can't just apply them anywhere. You have to hope that you see these structures somewhere and then apply them. Um, but it happens that these structures are very common, so these are actually very useful decompositions. The cats, so we'll come back to these. And then people have come up with even more decompositions by using these star edges. Uh, and then likewise, this is the same idea here, except it's represented with H boxes, which the zero H box is just the same as a star edge. Um, so yeah, so people have come up with lots of these new decompositions with lower and lower alphas. Some generally applicable, some applicable to specific structures. And then an obvious question is, how do people come up with these? Because if you look at something like this, you can think, like, where does this come from? It looks a bit chaotic. So one method, perhaps the most common method, is by simulated annealing. So I won't go into too much detail, and there's a few ways to approach this. But broadly speaking, you come up with sort of an initial guess of a decomposition, and then through like a random walk, you optimize these weights, and if it improves the fidelity, so it's more accurate, then you accept it with some probability. And if it makes it worse, then you're much less likely to accept it. And then this balances out, and then you end up finding these fancy decompositions. Um,
Matthew,
yes.
as as a question about that algorithm, I'm not sure in how much detail you've looked yourself at this algorithm. It always struck me as kind of magical that this works at all because the stabilized decompositions are so discrete, and it wouldn't seem to me that you can sort of continuously find your way to these discrete solutions. Do you have any intuition for like why this algorithm should work at finding like
Um,
any decompositions at all?
It is quite surprising. I've never implemented it myself because I've kind of gone with other approaches. So I don't really have much intuition for why it works so well, other than the fact that the data bears it out and it just does work very well. Um, but yeah, I see what you mean in the fact like it's all discretized, so it doesn't seem like it would make much sense to work, but it does work, and then that's the main thing here. Um, so Thomas Lakinen's thesis goes into a lot more detail on this, um, and he explores a few other methods as well. So he tried a genetic algorithm approach for trying to find new decompositions, but he concluded that that didn't work very well. So there's a lot more to be said there about methods that do work and methods that don't work, and how you can find these. Um, but yeah, so yeah, so last year Alex and I had this paper out at QPL, um, where we kind of turned this on its head a bit. And instead of trying to find new decompositions of lower alpha, we just take this very simple, like perhaps the most simple decomposition, the cutting decomposition, um, which if you apply this to a T-spider would have an alpha of 1, which is terrible. But we consider very specific places where applying this can actually be very effective. So here, as a very simple case, we have a T C naught T structure. So this C naught is the only thing blocking these two T gates. So if we actually cut this top vertex, then we end up with two terms, which both reduce to Clifford after simplification. So in this case, since we're cutting a Clifford spider, the alpha is actually infinite. So it doesn't help at all, essentially. But the effective alpha is 0.5. So if we consider the simplification that would be facilitated by it, the actual effective alpha is much more reduced. And then likewise, if we were doing this to a T-like spider, then they would go from alpha of 1 to alpha of 1/3. So then the idea here becomes, how can we find heuristics that tell us how likely it is that applying this decomposition in certain places is going to lead to more simplification to lower that effective alpha. And in this paper from last year, we considered this weighting heuristic where we apply weightings to these kind of structures, these T C naught T structures, and then we kind of propagate these weights out. And that worked fairly well. In this current paper that I'm talking about today, we kind of formalize this a bit more and trying to find more structures, some more specific use cases. So essentially, we're looking at special cases where the cut and decomposition leads to a lot of simplification. And then we express these as what we call dynamic decompositions. So this is the paper in question. And then what we show here is we come up with 4 of these new dynamic decompositions, and then we have a general heuristic for how to decide which one to use at each step, and then we benchmark this against the current state-of-the-art approach. And then I talk about a couple of extra decompositions which we tried out but didn't work very well. So the very first example here, then we have this decomposition 1. So this is the derivation here. So essentially, if we have a spider, and this could be Clifford or T-like, and it has a lot of spiders connected to it that are only connected to it and nothing else, then instead of applying, say, the magic 5 decomposition or any other decomposition, you could just cut this spider, and you'd lose that T count, and you'd lose the T count of all these spiders, which would now become just isolated scalars. So this will give you an alpha of 1 over n plus 1, that should be in this case, unless this is Clifford. And then we have a second decomposition, which is quite similar. So this one is if we have a chain of cat3 states that are all connected to a common vertex, instead of applying the cat3 decomposition to any of them, we can actually usually do much better just by cutting the common vertex. Because if we cut this common vertex here, I hope you can see the cursor of this one there, then all these other cat3s become cat2s, and cat2s, after simplification, reduce to 2 Clifford terms. So in this case, the alpha is 1 over 2n plus 1. And we call these decompositions dynamic because their alpha isn't just some fixed number. Their alpha depends on n, right? So the decomposition is expressed with these ellipses, so it's scalable to these kind of general cases. So these two...
You
Yes?
are showing these with like a 5 or 4 phase, but I'm assuming they work with any odd multiple of 5 or 4, right?
Yeah, I'll get to that. Yeah. So these don't have to be 5 over 4. It's just kind of easier to show the decomposition, but there could be any T-like phases. Yeah. And this bottom left vertex form that we actually cut here could be anything, but I think with the way that the structure is reduced, it'll always be T-like. But yeah, these can have odd coefficients. So these two we call the single decomposition because we're just looking at the graph and we're just applying one instance of vertex cutting. But a special case of, that's just vertex cutting, but we look at like a special case of where we want to apply it. And then we have two more decompositions which we call doubles because it requires one more step. So this one here, for instance, we have this fairly common structure that we sometimes see in ZX diagrams after they're reduced. And if we see the structure and we apply the pivoting rule, then it looks like this. And then once we have this, we apply one cut in the appropriate place, and it will reduce as shown here. So we call this double because it requires 2 steps, pivoting and then a cut. And this has a very good alpha here of 1 over 2 n plus 2. And lastly, we have this similar one here where we apply a case of pivoting and then a cut. And this has an alpha of 1 over n plus 2. So these are our 4 decompositions that we've introduced. And very briefly, I'll just talk about 2 more that we tried out. So this one on the left was one that after we implemented, we kind of realized that in Cozy's thesis, he already talks about this, but not in too much detail. The idea here is if you have multiple phase gadgets that have a lot of overlap, so a lot of their children are on the same vertices, then if you just cut the symmetric difference, so in this case, these 2 gadgets both are connected to the first 2, but the second gadget is also connected to the third, so the third's the symmetric difference. So if we just cut that, then they have the exact same child set, and then they can fuse with gadget fusion. And then on the right here, something kind of similar, where instead of doing a normal cut, sometimes it's more helpful to do this kind of separation cut. So we unfuse the spider and then cut the edge with the opposite color. So essentially it allows you to separate any vertex into 2 vertices, where arbitrarily one of them can have some set of the edges and the other will have the remaining edges. So we tried out these 2, but in practice, these just weren't that effective, even though they look fairly promising. And I think Alex helped come up with 1 or 2 of these. I can't remember which one. But yeah, we tried these in practice and they just didn't work quite as well as the others. So we've ignored these. And then the algorithm for deciding which ones to apply is very simple. So we know the alpha values for all the cat decompositions, so we'll just keep those in memory. And then we look for these structures, for these four dynamic decompositions that we have. And we just find the one that has the best alpha, essentially. And then we use that. So it's very simple. Heuristic, and I'll explain when and when not this heuristic is effective slightly later on. And then we benchmark this against the method of Kissinger et al. On these four types of circuits. So what we find, which is quite interesting, is that it actually varies quite significantly on which type of circuit we do. So instead of just considering a general benchmark, we kind of break this down by circuit class. So the first one is Clifford plus T circuits. So these are just randomly generated circuits with physics. So there's no structure to this. These are fully random. This is the gate set. So it's just Clifford plus T essentially. And what we find here, so blue is the existing method with Kissinger et al. And green is our method. We're only using the single decompositions, and then orange is using all four of the decompositions. So on fully random graphs, it basically makes no difference. You can maybe see like a slight marginal difference to the runtime, but really it had no effect at all. So we kind of just write that off. But these are fully random. Yeah.
Is the reason for that you just don't find these better decompositions very often?
Yeah, so in the case of just random Clifford graphs, well, these decompositions that we talk about here, as you can see, they rely on quite specific structures. Like this one requires a handful of Cat3 states connected to a common vertex. And if we're just generating the graphs purely random, then we just don't see these structures enough. There's just not enough structure in these graphs. But then if we consider Clifford plus T plus CCZs, then suddenly we do see a big improvement. So we do see these structures occurring very often. So here we see the effective alpha reduces by a big chunk when we add our single decompositions, and it increases roughly the same amount when we add the double decompositions on top as well. So perhaps this is unsurprising. So if we have circuits that have CCZs in them, if you kind of analyze these structures, you can kind of see how CCZs would reduce to this. And so it's very common to have the appropriate structures that we need when we have CCZs in the circuits. And so you can see here, it does make quite a significant difference to the runtime. So this is log 2 in milliseconds. So if we look at a specific example, you can see that it's gone down by a factor of like 5 or so for a T count 100. And all the T counts, the initial T counts are after an initial round of simplification. And this on the bottom right just shows the type of CCZ expression that we use. And then we consider IQP circuits. So IQP circuits were used as a helpful benchmark because they were considered to be helpful for benchmarking quantum supremacy circuits. And we measure these slightly differently by using the effective beta rather than alpha, which just only takes into account the T-spiders that aren't in the phase gadgets, because those that are part of the phase gadgets are just kind of trivial to get rid of by this method anyway. So this is just consistent with how it's measured in the literature. But again, we see an improvement. But what's interesting here is that on these types of circuits, which look like compositions of the bottom right figure there, we see that the single decomposition gives a noticeable improvement, but then these double decompositions don't really give much improvement on top. So it's kind of interesting to see how this arises, but it may be unsurprising because if you look at these structures, they're essentially just chains of cats, of Cat3s. And one of our single decompositions was essentially just optimizing 4 chains of Cat3, so it makes sense that it would optimize in this way. And then lastly, we have modified hidden shift, which is a specific type of quantum algorithm. There was originally hidden shift as a benchmark, but then that was proved to be trivial. So then it was optimized, or rather adapted to become non-trivial again with the modified hidden shift. So we just add these control swaps in. So it's Clifford plus T plus these control swaps, and that's how you generate these hidden shifts. And this is an actual quantum algorithm that's used. So this is quite a helpful benchmark. And here we see the opposite of what we saw just now, which is that the single decompositions don't really give much improvement, maybe like a marginal improvement, but these double decompositions do give a big improvement. And again, that's just from the way the structures relate to these the structures that we optimize in our decompositions relate to the structures of these circuits. And as for these gaps, that's just an artifact of how this data was generated. Likewise, for this graph, where it trails off at the end, it's just the fact that we generate as we increase the number of the depth in relation to the cubic count, it just gets a bit messy on these edge cases. But if you look at the general trends, that's what we're interested in here. So to summarize these results, we have for CCZ circuits, both sets of our decompositions give a big improvement, which is quite handy. And these represent random circuits, but that are structured, so kind of reasonable. Then modified hidden shift, these represent real quantum circuits. In this case, we've seen improvement with the double set of decompositions. And for IQPs, circuits which are useful for quantum supremacy benchmarking, apparently. It's slightly debated, I think. Our single decompositions are effective on this, while the doubles aren't. And then lastly, fully random circuits didn't really see any improvement, but these are the least realistic type of circuits that we consider anyway, so that we're not really too fussed about that. And this is essentially the conclusion of the paper. These are the summary. And then just as a brief note, so we can see that in each case, it almost never performs worse than the standard method. But sometimes on these very rare edge cases, you might see that it does actually perform worse. So we consider when this might be. So there are really two cases where this can happen. One is if the effective alpha of the new method is marginally lower than the old one, but the extra computational overhead of searching for these extra decompositions makes up the difference in the runtime, so it makes it slightly slower. But that's very rare because the alpha effective is usually significantly reduced. And then the other way is if our heuristic finds that if our heuristic is suboptimal in the case. So as I said, sure, if one of the new decompositions offers the best alpha and is chosen, but one of the other, say the cats might have led to, like the cat decomposition might have led to more simplification, but we just didn't predict that. But again, this is generally rare. Our decompositions tend to perform better. And this is the paper. And so these are the summary here of the results. And this is just kind of quite a small little paper, just benchmarking a couple of these new decompositions, just based on finding special cases of vertex cutting, essentially. So if you have any questions, I'll be happy to take them.
All right. Thank you very much, Matthew, for the nice talk. Do we have any questions in the audience? Questions, comments?
I have a question about earlier when you talk about the rewrite rules, like you demonstrated like a diagram that involves Hadamard gate at the bottom right corner. Where are those rules part of the
This one?
no, previous. Yes, the bottom right ones.
The bottom right. The bottom right don't really make any sense. Those are just ChatGPT redrawing this left figure, but it hasn't done a very good job in maintaining accuracy.
Oh, so this is not like an additional set of rewrite rules.
No, this is just a silly little picture just to keep it engaging. Yeah.
Okay, thanks.
Yeah.
So I had a question about your, I think the figures, the result at the end. You were comparing reduced T count, right? So you were doing the initial optimization step and not including the T gates that were trivially removable.
Yeah.
Okay. Cool. Yeah, I was wondering why these orange lines are so interrupted, but I guess you start with like a fixed number of Toffoli gates and then you optimize them, and this creates like a slight band of gates. But
Yeah, exactly. Yeah, it's just we could fill it in just by doing more data sets very precisely, but it is just a case of we increase the number of gates like in chunks. But if we took more data, we could fill in these gaps. But yeah.
How many qubits are these circuits?
I can't quite remember. Maybe I can check the paper. Yeah, I don't have it open. I can't quite remember off the top of my head. I'll have to get back to you on that one.
And like with the Toffoli gate, there's a trivial decomposition that reduces the 7 T gates and Toffoli to 2 terms. So I guess like your initial T count, it is considering like every toffoli times 7, but the in terms for the alpha, like I guess you could consider like the trivial case would be each toffoli gate introduces 2 terms. Like I'm wondering if you did anything with this information that you know that toffoli gate has this kind of decomposition. I know there was a
I
different
think
paper where they considered these decompositions.
yeah. So I think these just compared to like the blue bar here is just the Kissinger decomposition. So that's just the cat's decompositions and the magic five. So I don't think that takes into account uh, the Toffoli decomposition. Um, but there's some extent to which this is when you have multiple Toffolis and you reduce them anyway, that some of that is already lost.
Mhm.
Uh, but yeah, there's certainly more papers we could compare it against, which might be more effective than the Kissinger et al. Method. But that's just the one that's more generally applicable. And as I say, I'm trying to work on a more comprehensive benchmarking where I try to compare all the decompositions for all the circuit classes and stuff. Um, but yeah, it's quite tough to decide what to compare against, so we just pick this one benchmark.
So one of the benefits for like studying classical simulation you mentioned at the start is this knowing when the quantum advantage thing sort of happened.
Mhm.
But now the algorithms you find, like it looks like it depends a lot on the structure, right? So suppose I come up with a new method to that demonstrate quantum supremacy or quantum advantage. Um, like it might be I need to develop like new heuristics for simulating it because it might be that the things we have here don't actually work. So I might need to study this algorithm and find decompositions that particularly work well for that one. Like, is that one of the conclusions you can kind of make out of the data you get here?
In the sense of if we just take a quantum algorithm and we just run it directly classically, that might not be the best way of running it classically. Is that what you mean?
No, I mean like we saw, for instance, the completely random ones, they don't work so well. But then if
Mhm.
you have a particular type of structure, the single decompositions are very nice. But then for other types, you need the double decompositions. Like I could imagine a third class of circuits where like neither the single or the double work really well, but maybe there's like, I
Mhm.
don't know, it's like there's a triple one or there's like something else that you haven't considered yet, which then might trivialize that problem or make that problem much easier to simulate. So
Yeah,
so suppose someone comes up with a new way to demonstrate quantum advantage, or they claim it's a new way of quantum advantage, and then they benchmark it on these things, and they say, look, these things perform terribly, therefore it's hard to simulate. Like you could actually say, well, we know that these things work, like have like a different efficiency on different types of circuits, so we should really investigate these new class of circuits and find decompositions that are work particularly well for that one.
yeah, I think that's definitely the case. And there's a lot of that in the literature where like the Google claimed to have quantum advantage of something that would take like a million years, and then just optimizations to the way that it's classically simulated brings it down to like 11 days or something. Um,
Hmm.
and yeah, there are definitely more structures we can consider, and we don't necessarily want to consider all of these all of the time because if the more decompositions you have to search for, that adds an overhead as well. And especially if we had like tripled and quadrupled cases where you have to do multiple steps to try and apply this. So you might need some kind of meta heuristics to decide for your type of circuit which heuristics should we be considering. Um, so possibly that could be an approach to go, but it might get quite complicated. But yeah, definitely there's going to be a lot more of these types of special cases that are going to be found. And the way we just find these really is just by looking at examples of these different circuit classes and seeing structures that are common to them, and then just kind of by eye seeing that, well, this structure comes quite common, and if we apply a cut in this place, it leads to a lot of simplification. So also maybe a more formalized method of finding these types of dynamic decompositions could also be very helpful.
I could keep going asking questions, but maybe other people in the audience um, have remarks or comments as well. Okay, I guess I'll keep going then. Um, so these decompositions you didn't end up using because they didn't seem to be particularly useful.
Yeah.
So these look like phase gadgets that have like a lot of overlap and don't have overlap in like one point. So I'm wondering like whether quantum chemistry circuits might be good candidates for things where these kind of things happen a lot. because there you will have a lot of Pauli gadgets. And like there won't be pi over 4 in general, but like these methods don't care that things are pi over 4 anyway.
Yeah.
So then you just
Yeah.
have like a so you
Yeah, I
would have
think
a lot of Pauli exponentials, and then like you could even order them in such a way that you see these kind of structures happen very often, I think.
yeah, that definitely could be the case. We just tried this on the 4K full circuit classes that I mentioned, and it wasn't very often that you'd have a lot of these, or if you did have them, it would be quite small cases like this. But on other types of circuits, it might be very common. And then another problem is that it might be the case that you want to rewrite your circuit slightly to try and make it more common, um, which just adds kind of more heuristics you need to add to this, which is sort of what we were doing with the doubled, where you have your circuit and you need to do a little bit of rewriting in order to make it into a structure where applying the cut is helpful. But then if you need to do more than one step or two or three steps, then suddenly the complexity grows quite large. But if you keep it quite focused and you know which decompositions are going to be effective for which classes of circuits, then you can kind of keep it a lot more focused.
Mm.
And yeah, I can imagine there are certain circuit classes where this is a lot more common than the ones we tried.
So the observation you made at the end that the sort of kept the more complicated decompositions in like in our original paper. Um, yeah, that like you said like, oh, in which cases does this turn out to work better? And you said, oh, there are these rare cases where like the structure of the circuit changes and therefore it's like more optimal because the greedy search doesn't find the optimal path actually. Um, Yeah, so to me, this is kind of sad that this is the case because I was like our decompositions, like the structure that you get at the end is like quite random. So you're sort of scrambling all your daughter circuits, all your daughter diagrams that you get out of these things. So you get like a much more random array of diagrams. While in your techniques, I think it's mostly like graph minors, like you're removing edges, you're removing vertices. So it's a much more you can much more accurately predict what kind of diagrams you get out of
Yeah.
it once you apply decomposition.
Yeah, that's exactly
Um,
what this is based on the cutting decomposition, which I've got written somewhere in the general form. Yeah, the top right there.
mhm,
Because it's just a very neat decomposition. Any way you apply it, especially on these types of circuits, the fully reduced circuits where everything is just connected by Hadamard edges, essentially it just removes that vertex. So it's
mhm.
very easy to predict how it behaves. Whereas if you do
Yeah.
something like cats, it leads into, say, three different sub-diagrams, which can all be very different in structure. So it's a lot harder to predict.
Yeah, and so I guess like our hope was that this it's harder to predict, but like due to serendipity, it would result in more cancellations. But it looks like you're saying like, well, actually these really structured ones where you can predict what's going to happen, like those are much more useful because you can like very accurately predict if I do this, these T gates are going to get removed. I know this is a good thing to do instead of relying on this sort of serendipity.
Yeah,
Uh,
yeah. I mean, the cats ones are also very effective at producing circuits that have more cats in them, which is quite nice. I haven't done any
hmm.
marks of these decompositions that don't also use cats. So I don't know if I made it clear, but in this, for instance, the blue is cats and magic five. The green is cats and magic five plus the single decompositions. So we're still using
Hmm.
cats where it deems that to be more effective. Um, so I'm not saying this supersedes cats. This is just something that is helpful to add on top of the cat's decompositions.
Hmm. And so all this is greedy search, right? Like you look like one deep and you pick the one that's
It's
best.
like really search up to one step. Yeah.
Yeah.
Obviously, if you go more steps, the complexity grows exponentially, um,
Yeah.
which is why we
Have
want to
you
keep.
have you like looked at examples, like if you go too deep, like how much difference this makes and if it's worthwhile this extra complexity?
Yeah, generally it drops off pretty quick, we find, because especially when you have circuits like this where we know from the structure that this is likely to lead to a lot of simplification. If we look further steps ahead, we don't really see much of a difference based on that initial prediction, but it does increase the
Mm.
runtime quite drastically. So sometimes two or three steps ahead can be handy, but I think anything beyond that is just kind of wasteful usually. But then there's
Yeah.
always edge cases where it looks like it's not going to help much until you suddenly do 10 steps ahead and then it looks like it all comes together. But these are just kind of impossible to predict.
Okay. Okay, so I'm kind of done with my question barrage. But if there's no more questions from the audience, I maybe have one high level thing to sort of end on. Like you've now studied these decompositions and the simulation approaches with SEDEX for the last couple of years, and you've
Hmm.
implemented a lot of different techniques and methods. Like, how much do you feel there's still that we don't know about this, or like things that might make a big difference here that you haven't tried yet?
Yeah. So we're still trying new stuff, and I've got a couple of other like projects in the work. Mostly the one with Richie and Alex, where we're trying to use reinforcement learning to try because a lot of this is just kind of based on just eyeballing it and trying to see what works and testing and things. So we're trying to let AI kind of handle that for us. But then it's quite hard to interpret how it makes these decisions. Um, but it is an intractable problem. So there's always going to be more optimizations you can do there. And then it's kind of, I think what's less interesting is just coming up with new decompositions over and over and over that is like slightly lowering the alpha. And then what's more interesting is if we can find kind of new techniques altogether. Um, so last year I did some work where we do partitioning, and it kind of combines tensor contraction with stabilized decomposition, and that led to some interesting improvements as well. So I think more along those lines might be more interesting than just coming up with new decompositions all the time. But I think there's always going to be improvements people can find. It's just kind of a trade-off between how much search you want to do versus like how much improvement you get.
Hmm. Okay, very nice.
Can I follow up?
Yeah.
Have you looked at like the decomposition output from your deep reinforcement learning agent and kind of look at why they always make certain decisions?
Um, that is something that we're planning to do, is to kind of analyze how it makes these. But at the moment, we're just trying to get it to give an improvement. So the problem we have right now is that with all the training that we're doing on these, the reinforcement learning, and we've tried a transformer-based method more recently, the improvement we see is kind of um, marginally better than the heuristics at best. Usually it's about the same as the heuristics, or slightly worse. So it's quite hard to actually improve even using machine learning, because the heuristics we have are very effective. But right now we haven't taken into account all these decompositions. It's just trying like the magic 5 decomposition. Um, so I don't have the graph on me here, but um, maybe I can find the decomposition. Yeah, so this one at the top right. So in the paper with Kissinger and et al. And John, etc., it uses these decompositions wherever they're applicable, and then it falls back on this one on the right when there are no cat states, and it picks these 5 vertices randomly. And so what we try to do is instead of placing them randomly, we motivate that choice using reinforcement learning. But we found that it's kind of only gives a marginal improvement versus doing it randomly. Um, so it's also kind of trying to figure out where we should be applying the reinforcement learning as much as the fact of applying it. So it's really quite hard to get past this stage. And then eventually we want to kind of analyze how it's making these decisions once it is making very good decisions.
Is
But the
it
struggle
because,
is this, there might not be that much room for improvement in some of these cases.
right? Is it because like using the heuristic is achieving the close to optimal performance, so then it makes no difference between using deep reinforcement learning or just human
Yes.
inspired approach?
Yeah. So given like an action space of a certain class of decompositions. So say for instance, if we're just using these cast decompositions and this magic 5 decomposition, then the heuristic method is pretty much always very close to the actual optimal method that exists. So there's not really much more improvement to be made, even if we could find better optimizations. There's just not much more improvement to be made there. But then that might not be the case when we start bringing in more decompositions and stuff, where things get more complicated. But in the simple cases we've been looking at so far, it's just that these heuristic methods are already pretty close to the optimal that you can get, um, until we add more decompositions.
Thank you.